Good afternoon, everybody. Indeed, I will be speaking about extreme performance with regard to the transformer as we're here at, let's say, the generator and transformer business event. A quick overview about what I will be speaking about. First, short introduction about the organization I'm working with and why we are coping with wind energy research and development, some drivers. A little bit about technological evolution there as well and the technological challenges that we have. Then I go straight to the risk mitigation strategies. On one way, I will tell something about the requirements, and I will mainly focus on cold climate, but also on another strategy, more looking into testing and validation. Again, focusing on cold climate. And then to finish, I will talk about the testing of some transformers, which we do in our laboratory. One hand, I have a case of a liquid filled transformer, and on the other hand, I have a case about a cast resin transformer. So I'm working for a Belgian non-profit research organization called CIRIS. We cope with multidisciplinary research projects, innovation projects. Our main goal is to support and implement technological innovations at Belgian companies. One hand SMEs, on the other hand large companies. But we also participate in European projects, funded European projects where we work, of course, together with different knowledge centers across Europe and some other companies as well. And to do so, we have 106 engineers. You could compare us with the Fraunhofer, but then in Belgium. But of course, we're a small country. We don't have that much engineers as Fraunhofer does. But we do have some high-tech research infrastructure, and one of the test laboratories, which I will explain, is a large climate chamber, which is quite unique in Europe to do some research in that field. So we have different competences ranging from software engineering to materials research and so on. And I'm working on a dedicated application lab. So we have different application labs. We have 4 of them. We're making a 5th as well. And there we focus on a certain technology, for example, our composites lab, or a certain application. And in my case, this is wind energy. We more specifically focus on offshore wind energy. Why? Onshore wind energy is maturing. For offshore wind energy, we still have a big gap, a technological gap. Still, we need to do a lot of research and field measurements in order to see how these systems are performing in the field. And what we did 4 years ago is we did an investment program, about 6 million euros, which we invested in state-of-the-art test and monitoring equipment in order to gain data sets from laboratory testing on transformers, for example, but also gearboxes and other components. And on the other hand, monitoring equipment in order to gain field measurements about how these components and the turbines are performing in the field. And this we use to gain insights and information which we can use for new innovation projects. One thing I will be talking about, and one investment that we did, is one of the largest climate chambers in Europe to do mainly a focus on extreme cold and hot temperature testing. So these are validation tests on transformer. The unique thing about this test facility is that we can cope with more than 150 ton heavy machinery inside this climate chamber. The foundation is 40 ton per square meter, for example. And we can cool down heavy machinery down to minus 60 degrees. In the hot climate range, we can do testing at plus 60 degrees. And it's quite large. Here you see a 5.5 MVA transformer, so that's not a really big one, but we can have a larger one as well. And also one of the beneficial things about the large climate chamber is we can do multiple testing in one time. So in a couple of weeks, we will do some testing, 3 transformers in one time. We focus on wind energy components mainly, but as we are working on multidisciplinary projects, we also cope with other industries, like, for example, off-highway and so on. The second investment was about investing in state-of-the-art monitoring equipment, and like you can see on the picture, I'm not always wearing this suit. Sometimes I'm wearing the wetsuit to go offshore, and this is to do some research in the field to gain knowledge about, for example, vibrations on transformers, on the tower, and so on. But also we are validating some new sensor techniques there. One sensor there is a corrosion sensor, which we are validating to see if we can use that technology for offshore asset monitoring. The data coming from the lab and from the field, we want to use to gain knowledge. And why do we need this knowledge? On one hand, we want to reduce the capex, so that's the investment cost of turbines and their components. On the other hand, we want to reduce the opex, that's the operation and maintenance costs, as in offshore This is 2 to 3 times higher than we have in onshore applications. And we want to increase the yield of the turbine. So we're looking into more efficient components as well. And coming back to these, actually the drivers for this research, here you can see how we calculate the levelized cost of energy. So in general, we want to have a lower levelized cost of energy. And one of the targets there, for example, Dong Energy is one of the biggest players installing offshore capacity, is €100 per megawatt hours, which they want to reach at, in 2020. At this moment, this is nearly 175 to 190 euros per megawatt hour. So still, there is a big task to do to lower down the costs. A figure from EDP, that's a utility in Portugal. Here you see that onshore wind energy is already competing with conventional power plants. So there already we have some technological evolution. But if you look into the offshore technology, still we need some work to do. Looking back at this, the formula for the levelized cost of energy, one thing is the operational expenditure, so the operation and maintenance cost. And one topic which is very important there is reliability. Reliability, that means the ability of a system to perform a task in the given environmental conditions and operational loads, and that for a certain amount of time. And with regard to time for wind energy or a wind turbine, we are developing these machines for 20 to 25 years. So reliability is very important there. But also we don't want components, of course, to fail early. We have the maintenance cost, but on the other hand, we also have the annual energy production. And reliability with regard to availability, for example, if we have a component of only €100 which fails and the weather is bad, it takes a long time to replace this. You cannot just go with your car or with your boat like we do it in onshore technology. You can go with your car to there and you're there in 1 hour for the service technician. In offshore, this is not the case. If the weather is bad, you have to wait. And because of this, you also have a downtime. And this downtime can be nearly 5,000 to 15,000 euros a day. So this is something to take into account. We have to have reliable components on every level. So it's not only for the big components, the gearboxes, the transformers and so on, but also the small components there, sensors and so on. So also for sub-suppliers of transformers, for example, we have to make sure that every subsystem is reliable in all conditions. And maybe you think downtime, well, this is not happening quite often. I want to say something about an article I read in January. And I want to stress January because this year we had a very good windy year. Winter time is typically the best time in seasons that we have for wind energy applications. There we have a 62 megawatt wind farm T-site, and they had to shut it down for 1 month because there had been some vibrations which they didn't expect on certain housing in the tower. So they had to shut it down, not because there was a failure, but there were some vibrations. And also health and safety is very important in this sector. So it was shut down. I'm not sure which component it was, it doesn't matter. But the turbines were down for 1 month, and then after 1 month, half of the capacity was on the grid again, but still they didn't know what happened. So this stresses the need for more research in this field. With regard to transformers and the main components in such a turbine, a transformer is one of the most essential equipment in a turbine. I will come back to this later. And a study that I found is nearly 10% of the failures of components are related to the transformer, 13% to the generator. It depends from wind turbine to wind farm. I think more studies have to be made about the reliability of the components. But nevertheless, the transformer is an essential part of the wind farm. You see them in the towers or the nacelle of the turbine itself for distribution. But you also have these big offshore high voltage substations which step up the voltage to a higher value in order to have the distribution in an efficient way. If your transformer there is failing, then you have a big problem. And here on the bottom you can see the downtime. If you want to replace such a big transformer, you don't have this off the shelf. It takes quite some time to have a new transformer, 5 months to 1 year. So again, you have a big downtime there for a whole wind farm then. In the beginning of this industry, they used off-the-shelf distribution transformers. So now I'm talking about the transformers which are located inside the tower, in the base tower, or in a nacelle. And actually the duty cycle which we see in wind energy applications, so it's very variable. they didn't match with the designs for the transformers. Also, the environmental loads, the environmental conditions, certainly offshore, are much tougher than what we see in onshore applications. And in the beginning, we had some defects, some examples there: fires, lightning, leakage, cracks in the cast resin transformers. And actually, the technology is maturing by trial and error onshore, and maybe we will see the same now for offshore as there. And I will stress this in the next slides, that we see some extra environmental loads there as well. Nevertheless, it takes time to reach a mature technology. By failing, we will learn, and I think every industry is having this struggle, let's say. If we compare it with the aerospace industry, the brothers Wright in 1903, they didn't have a perfect plane, but if you see these developments, which you see now, the Airbus A380, which had its first flight in 2005, you have 102 years of development, continuously technological evolution. Coming back to offshore wind energy, the first offshore wind farm, which was rather a small farm, only 5 megawatts in Denmark, only 2 kilometers out of shore, only small turbines, 450 kilowatts, that was installed in 1991. And if I'm looking at our Belgian waters now, there we have 6.5 megawatt machines, state of the art, spinning there, a 325 megawatt wind farm. So this is only 22 years of development. So we will have some time still to mature, and some failures will occur, but we have to mitigate the risks, and we have to take it into account already now, if we can. Looking at technological evolution, there's also a big challenge for the manufacturers, not only the OEMs, but also the component manufacturer, and maybe as well for the subcomponent manufacturers. The time to market is very important. This is a rapid evolution that is going on in this sector. In 2012, we were talking about the 6.5 megawatt, now already there in the waters. And if you look at 2014, for example, Vestas, Mitsubishi, they all have their new prototypes. It's already 8 megawatts. On the left side, you can see the cathedral of the city where I live. If you compare this to these huge machines which are spinning in very harsh conditions, this is a technological evolution. And to begin with, we have to optimize what we have in the field. But already there are some companies who are looking into radical innovations. For example, on the right-hand side, you can see wind turbine design of a Dutch manufacturer, 2B Energy. And they are using a 2-bladed wind turbine instead of 3-bladed. So why is this? We are using 3-bladed turbines because of the sound and the technology of wind energy. It matured onshore, so they said, okay, we have a mature technology, let's place it offshore. But actually a 2-bladed turbine is maybe better. Sound is not a big problem offshore. And also with regard to electrical components, we used to install them in the tower base, in the midsection of the tower, or beneath, or in a nacelle. But as we see capacity increasing, and with regard to the maintainability, as the operation and maintenance cost is very important, they tend to place them outside on the platform. And already there you see the first prototype, so it is going very fast. Some designers are having scope of 40-year lifetime instead of a 20-year lifetime. So this is stressing the evolution that is being made in this industry, which is interesting. So here an example about the electrical equipment, switchgear, transformer, electronics outside of the turbine because of maintainability reasons. Now the focus, how can we mitigate the risk? First thing is we have to look into the requirements. We have to need exact, realistic requirements, and therefore you of course need to have public field data. It all starts with the requirements. If your requirement is not set good or correct, this will translate itself in the acceptance testing and so on. So here you have this product development cycle. And I want to stress the requirements. Looking into environmental loads, with regard to the requirements, you have different loads there. You have extreme temperatures sometimes, you have wind gusts, you have lightning, you have extreme waves in some cases, and all these things have to be taken into account. And it's coming, but still there is some extra to be done. We divide these environmental loads. On the one side, we have the mechanical loads, This is, for example, as well the low frequency vibrations coming from waves, extreme wave buildup, earthquakes in some cases, but that's more onshore, for example, Japan region. And we have the climatic factors. And on one hand, with the field measurements, we are coping with the mechanical vibrations on the turbine and the platform. In the laboratory, we are doing the climatic tests, mainly temperature, a little bit humidity. The others, we are not focusing at this moment. And to give you some examples, to stress this, a normal wind turbine in the Belgian North Sea, well, there you have this operating temperature of -10 to +40. That's not that extreme, but you have some other sites, the northern Baltic Sea, where you can have -30 degrees. So your components, if they're located in the tower or on the platform, they also have to withstand these temperatures, and it has to be taken into account. Again, we see some development in the Arctic, -35, and an extreme example that's -50 degrees, that's in Mongolia overnight. It can occur. We also have done some testing at -60 already for the Russian market. So these are really extreme events. And things can go wrong. If they go wrong, they will lead to a big downtime, because the maintainability in such sites is very harsh and difficult. Looking into vibrations, for example, this is a picture of an offshore voltage station and some extreme waves during stormy weather. In our research turbine that we have in the Belwind wind farm, we have a partnership with one of the wind farm owners. We have installed a wave radar now in order to see how these waves are building up. And it's also part of a European joint industry project called OWI-Lab, where we're looking into the behavior of such wave buildup and the impact on the wind turbine. So we have installed a lot of accelerometers on this turbine to see how dynamic this system is. And actually, it's a very dynamic system. One of the interesting results is also you have certain events. So you have this variable wind pattern. And if you look at the fundamental vibration modes, here you see the vibration modes when the turbine is in operation. When the turbine is standing still, you see some other vibration modes, which is very interesting to take into account, as in operation you see the turbine vibrating like this, but maybe in standstill the turbine is vibrating like this with regard to wave impacts and so on. And this is something which also has to be taken into account for all the components which are inside the tower and so on. Certainly when we're talking about the next revolution of wind turbines which are floating, you already have these prototypes, and here as well you can see that the electronics and the switchgear and transformer are installed on the platform, and therefore you also will have to do some inclination tests, because this will be a more dynamic system than a fixed foundation. It's not only the operational phase that matters. You manufacture a product, it will be shipped, it will be transported, sometimes it's stored for a couple of months, and during installation it also sees some impacts. So also this has to be taken into account. When we look at our climatic testing, the first thing which we do is a storage test at a much lower temperature than the operational test. I will come back to this later on. And again, an example, this is the Haliade 6 megawatt installation from Alstom. In some cases, when you're installing, the weather is very bad and you have a downtime for installation people of 3 weeks, which means that if you have installed some components already there, and the winter time, you can have some condensation, or it will become very cold inside the tower. This has to be taken into account as well. Something about hot climate, there most of the time we have a +40 degrees specification or +50, and it was a very interesting winter time, let's say. On one part of the world we had very cold freezing temperatures, and on the other part of the world we had very hot temperatures, so 46 degrees in Australia. So taking hot climate as well into account matters. Certainly for Mongolia, there you have very extreme cold and very extreme warm temperatures. So the delta T is very large and has to be taken into account as well. So it's a challenge for wind turbine manufacturers. The wind turbines are installed worldwide, and therefore they're subjected to all kind of environmental loads. So we have classification. On one hand, we have this wind speed classification. On the other hand, we have the climatic specification. You have just the normal onshore wind turbine, let's say. We have the hot climate version, we have the cold climate version, the offshore version, and sometimes we merge them as well. Then we have an offshore cold climate wind turbine. I will mainly speak about the cold climate. There are some certification guidelines. For example, GL has some, and it states that, for example, a normal turbine, it should be spinning or should be operational until minus 10 degrees. For the cold climate version, that's minus 30 degrees. And from then, we stop the turbine, and it's standing still. It goes into a survival mode, and it could withstand minus 40 degrees ultimately. But I want to stress one thing. First thing, wintertime is a very good period to have production, to have yield. So maybe if you're located on shore and minus 15 or minus 12 degrees or minus 16 degrees happens quite often, then you will lose production. And also, looking into cold climate version turbines, one fact, and that's written by Ian a couple of months ago, such wind turbines, they produce 11% more power at minus 10 degrees than in the positive range of plus 20 degrees. That's because of the air density is much higher, so you can have more yield as well. So wintertime and having a high availability in wintertime is very important actually. With regard to transformers, of course, they take this into account. Sometimes they even go to much lower temperatures to test. With regard to the cast resin transformer, I will finish later on with the classification. You have C1, C2, and also C3. Looking at 2014, we had some special events. So GL states minus 40 degrees, for example, but in some parts of the world we had some extreme weather events. Mongolia, minus 50, I already said that, but also Canada, minus 49 in wintertime because of the polar vortex. And what was interesting this morning, I was sitting on breakfast and I saw this article, hot, cold, why the wacky weather? And it seems to that global warming is causing new wind patterns high in the sky, which lead or could lead, it's not proven yet, but to more extreme weather events. And that's not typhoons and storms, but more extreme cold or warm conditions, more dry or more humid conditions. So let's see, maybe I'm right, maybe I'm not, but maybe in 20 years we will remember this slide. The second strategy and the focus actually is test and validate for all conditions to find weak spots and to prove the reliability. And also this is a trend in wind turbine industry. Manufacturers, knowledge centers are investing quite a lot in state-of-the-art test equipment in order to mitigate the risks which are associated to environmental loads. Lightning test facilities, for example, blade test facilities, and for example, Fraunhofer and Narek, they're installing big test rigs to simulate wind gusts on the drivetrain, for example. And also the operational limits we should test, but also the extreme events. This is an example from Minnesota. If it goes wrong, it tends to go very wrong. This turbine, they had minus 20 at that site. The steel was not specified for that. In combination with high wind gusts and poor welding quality, this was the result. And again, failures happen. The Challenger was also related to a cold weather problem and a faulty design of an O-ring. Also in defense, the Liberty ships in World War II, they had some cracks, and that was also because of cold weather with regard to poor welding quality. And there have been some problems in the field as well with transformers. There has been leakage, whether it's related to vibrations, climatics, we don't know yet, but that's why we are doing the research. Right-hand side is a crack because of extreme cold on a resin cast transformer, because the material becomes very brittle, and then if you have a thermal shock, you can have these problems. How can we mitigate it? Testing. Environmental testing. One hand, you can just do the climatic testing, for example, for corrosion. On the right-hand side, you can only do the vibrations on a vibration table. It would be better if we combine them. What we do, for example, in our laboratory, we place, for example, a wind turbine transformer inside the climate chamber. We cool it down to a very low temperature, minus 30, for example. And then we put full load on the transformer. In the case of a liquid filled transformer, we have a pressure increase then, so extra stresses on the tank, and in that way we can check if any leakage will occur or not. And this is the development research test. We can also do some endurance tests, but it's not an end-of-line test, to stress. You will not test every wind turbine transformer or transformer for other applications every time. It's development. How do we cope with this? So we have this very large climate chamber, and why are we doing this? On one hand, I already said this, in comparison to conventional power plants, which are more like in controlled conditions. Wind turbines are subjected to extra stresses from environmental parameters. One extreme event is the cold startup. And to mitigate this, we will do some testing. You do overstress testing, you do fatigue testing. You will also simulate, but you always have to validate simulation models. And sometimes simulation can be quite complex, time-consuming, and time to market is one of the important parameters. And last point is sometimes it's just required for certification. The challenge there is you need state-of-the-art test infrastructure to do so. It's a big investment. You can do this, you can invest in it, but if you look at the trends for wind energy, one of our customers, they tend to do it in a cooling container, but because of the multi-megawatt components, they couldn't place them inside such containers anymore, so they needed a bigger chamber. Two cases to finish. The liquid fill transformer. Why do we do this test and what do we do? First hand, I already explained this. This is the storage test at -40, so we check leakage, we check if there is any visual impact on the bushings, the cables and so on. And afterwards we do an operational test at -30 degrees, for example. Then again we check for leakage and we also check the cooling performance, so the natural cooling convection. The research, you can find it online. It's a shared paper between CG Power and OWI-Lab. So the first thing, leakage, what can happen there if you have a liquid fill transformer, also with a gas cushion, for example. You cool it down, you can have under pressure. This is one thing we check. But if you put load on it, it will expand again, and that's why we check if there is any influence, if there are pressure peaks and so on. The second thing, what we want to test, you would imagine if you have this very cold temperature that cooling is not a problem, but it can. Why? The oil, the cooling, the electricum, it becomes very stiff, and it could be that it loses its performance for natural cooling convection. So we need to put the heat coming from the windings to the fins of the transformer, and because it's a very stiff oil at that moment, we have to validate if this is actually really happening. That's why this is to mitigate the risk and to be sure that the design is right. And this is very complex to simulate, that's why you test this. The approach, so this is a climate chamber, we put the transformer inside it. We are using an intermediate multi-tapper transformer there in order to supply different voltages, because sometimes we have a smaller transformer, sometimes we have 50 Hertz products, sometimes we have 60 Hertz, and we apply a full load on the transformer. How do we do this? We put the short circuit voltage on the high voltage bushings, and the low voltage bushings are short circuited. In that way we can have the nominal current flowing into the transformer. When we put up the generator is placed outside, and we can put multiple generators in parallel if we have big transformers, or we even can use a load bank for certain testing. Finishing with the cast resin transformer, again this is also one of the cases we did at very low temperatures. We have a partnership there with DMV CWIEME in order to cope with very extreme temperature testing of these cast resin transformers. The main thing which we check is are there any cracks because of the brittle materials and the thermal shock. And as I explained, yet you have some classes there, some certification classes. C1 that's not that tough, -5 operational, -25 storage. You have C2, which is -25 operational testing, and class 3 is not really an official class, I think, but some manufacturers, for example, for the Russian market, they want to test at -40, -50, or -60 degrees, and then again also you do the storage test at these temperatures. And because of the variable wind pattern and also the brittle material, you can have cracks, some examples which could lead to partial discharge in concentrated areas, and this is again a risk for the transformer, so that's why we are testing and validating this in the laboratory. To conclude, I've said something about reliability. This is key for the industry, certainly for offshore, as the maintenance cost is much higher there. Maintainability as well is very important. It's a fast increasing technological evolution that we see in the market. The turbines are installed in different sites. I've showed some examples with regard to that. We need field data, we need laboratory data in order to mitigate these risks. And I have shown some examples about how we are doing this in the laboratory and what we're doing in the field. So thanks for your attention. If there are any questions, please shoot.
Well, thanks very much, Pieter, because not only were you almost completely on time, but you delivered a great talk with some probably the best photographs we've seen so far today. So in the time we've got left over, does anybody want to ask a question or make a point, please? Yes. Maybe I could ask you something. Is any of your work now applicable to the even newer technology in terms of the reliability of wave energy? Do you work at all in wave energy? Are some of your ideas applicable to that as well?
Well, probably for wave energy and tidal energy, we will have the same challenges there for the electrical equipment, as this is also near shore or offshore. But I haven't seen any of these applications so far in our laboratory, but there is one Belgian project, it's called Flancy, where they are developing such a wave converter, and they also want to use this in Belgian waters for validation. So maybe in the coming months we will see something about this, but I'm not sure. But again, the reliability will be the same big topic for such harvesting.
Anybody else want to say anything? Well, look, if not, we've had a very full session, so we'll draw it to a close now. And thank you again, Pieter. And we'll be back in another 15 minutes or so for the next session. Thank you.